Hello my dear students. So today we will be discussing about quantum mechanical model. Okay, so in the last class we have discussed Heisenberg's uncertainty principle. So where we have studied that we cannot find exact position and momentum of a particle which is under motion simultaneously, right now. Okay, it means there will be some error while we are calculating or we are measuring the exact position and momentum for a particle which is under motion, like particle like electron, microscopic particles, right now. Yes, so now this is a main foundation, I can say, or basis for the quantum mechanical model of atoms. Here what is the significance of uncertainty principle? See, here this uncertainty principle, see, rules out the definite path of the electrons. See, in Bohr's atomic model we have studied that so electrons are revolves around the nucleus in circular path, defined circular paths, right now. So this like Heisenberg uncertainty rule or hypothesis rules out this existence of definite particle, as it is saying that there is no we cannot find exact momentum or the velocity or the position of a moving particle right now simultaneously, right now. So it means here he introduced that we cannot find exact position and momentum, but you know here he given a new statement that we can find the probability of finding an electron in a region. The concept of probability of finding an electron is introduced in the place of this certain definite paths in which electron is present. Okay, so this is the we have studied that contradict to the Bohr theory and all, no? Yes. Then next, precise statements. See, there we are saying like precise statements of position and momentum of electron is replaced with the probability. There we are saying certain circular paths, definite circular paths, we are saying that will be now replaced by what terms? By probability term. So what we are saying now, probability of finding an electron is maximum in a given region around the nucleus, and this statement is now considered as a what called orbital. What is an orbital now? Orbital is a region, three-dimensional space around the nucleus where probability of finding an electron is maximum. Okay, so now orbital in the case of Bohr's atomic model. Now here we are discussing about orbital. In that case it is orbit. Okay, orbit is circular path, we have discussed it there. Okay, here I am saying orbital. This is a three-dimensional space around the nucleus. Probability of finding an electron is maximum in that region. Okay, now this statement here, the probability of finding an electron is maximum, we are saying around the nucleus. So these kind of statements are the basis of quantum mechanical model. Okay, so now quantum mechanical model, what are the things considered? In a Bohr model it is considered as particle nature now. So in the particle nature of electron is considered there, but in the quantum mechanical model, by considering like Heisenberg's uncertainty principle and de Broglie's wave nature, these things, by considering these things, our quantum mechanical model has been introduced or started, I can say. Okay, now we have an equation called Schrödinger wave equation. Okay, that is indicated like this: dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square e minus v psi equals to 0. So here you can just use this Laplacian operator like del square. Okay, so this indicates what? Dou square by dou x square, those things are there now, that is indicated by this. Dou square by dou x square plus dou square by dou y square plus dou square by dou z square is simply indicated with del square. Okay, so into psi plus 8 pi square m by h square e minus v is equals to e minus v into psi is equals to 0. Okay, in this way also you can write, you know what is E here? It is total energy and V is potential energy of that electron here, and psi represents what? Psi is called wave function here. So what is that psi? Psi is called wave function here. Okay, just a minute. Psi is called wave function. So what is this wave function? See, upon solving this equation, we will get the solutions of this particular equation. So that is what the psi is indicates what? So this psi has or includes all the information or the dynamic information about the electron, where the electron is present. okay, and what is its energy, like this, and what is the shape of that particular orbital in which this electron is present, or at what distance, or I can say in what is the size of that particular shell in which this electron is present. All these kind of informations are there in this site. The solution of Schrodinger wave equation contains all those information. Okay, now this equation, and also this is expanded equation I can say, and we have one more reduced equation like this: Hamiltonian operator H psi equals to E cell. Okay, so here it is, E is called here what? Energy. This energy, or in other terms I can say eigenvalue. This is the standard representation of eigen equation. So E is called here energy in this case. Okay, yes, yeah. So let us move forward with one more. So what I told you, wave function psi, it is a solution of Schrodinger equation. So now by solving that Schrodinger equation we got solutions. Now we will get solutions. Okay, the solving of that Schrodinger equation is not in our syllabus, but just imagine that we have solved the Schrodinger equation, we got some solution. Now all the solutions were not accepted. There are some conditions to be accept the solution. Okay, what are the conditions? But solutions are not accepted. All solutions are not accepted. Only those solutions are accepted which have wave function must be continuous. What do we mean by continuous here? For example, I have a wave function something like this. Okay, so this is something like continuous wave function right now. So now I am writing one more wave. I am indicating something like this. Something like this. See how it is? It is something like discontinuous now. So in this manner you can understand. Okay, it should be continuous and it should be finite and it should be single valued. Wave function must be finite, continuous, single valued, and see here first derivative of wave function must be continuous. These are the four statements should be satisfied in order to accept the solution comes from that Schrodinger wave equation. Okay, so these are very important points that should be remembered, because in the exam they will ask based on these four statements only. Okay, yes. The next, so how do we solve this wave equation, wave function? See, as of the syllabus, if you see, there is no solution for Schrodinger equation from in our syllabus. They won't ask, but you know, you should have some basic idea. See, Schrodinger wave equation is solved to get the values of psi, that is what? Wave function. Okay, now this wave function will give us the detailed information, the complete information about the electron, where it is present and what is its energy and all those things. So psi is a wave function that contains dynamic information about the system I am saying. Okay, so now this Schrodinger wave equation can be solved for hydrogen like species. Okay, if you want to solve for hydrogen like species, we need to use something like spherical polar coordinates. Normally we know Cartesian coordinates now, so x, y, z axis we are taking. Okay, so similar to that, here we will be using spherical coordinates. Okay, in these spherical coordinates, like x, y, z axis are there now, so those are considered like x axis here r sin theta cos pi, and y here I am taking r sin theta sin pi, and z axis r cos theta, like this we will be taking. Now the Schrodinger wave equation or the wave function will be having two parts. One is called radial part, another one is called angular part. So this the wave function or this psi contains what now? So one is radial part and another one is angular part. Okay, I will be showing you this. Okay, so like this. See, this is the consideration of spherical coordinate. See, it contains one pi part here you can see, and here one theta part and one radial part here. Okay, so now I will tell you what exactly this radial part and all. See, the wave function contains two things. One is radial part, another one is angular part. From the radial part, you will be getting quantum number n comma l. So what are these quantum? These values of n and l comes from this radial part of this Schrodinger equation for hydrogen atom. Okay, so this is radial part which gives us quantum number l, n and l. And whereas we have one more part is called angular part. So angular part again it will be theta part and pi part. Okay, from this we will get L value and ML value. So how many quantum numbers we are getting from Schrodinger wave equation? We are getting 3 quantum numbers. What are those 3 quantum numbers? One is like this principal quantum number, I will tell you what is that principal quantum number, and another one is L, here and here both is giving L, okay, that is azimuthal quantum number, and third one is what, magnetic quantum number. These are the three quantum numbers coming from Schrodinger wave equation, and you know we have total 4 quantum numbers, but only 3 are from Schrodinger wave equation, I mean this solving this equation, and the fourth is one added from outside, that is not from this equation. Okay, hope it is clear. So we are getting only 3 quantum numbers from this wave function, N, L, ML. These are the only 3 things. Okay, you should remember this point also. Okay, so now what exactly an orbital here? What exactly an orbital? See, orbital is a 3-dimensional region around the nucleus where probability of finding an electron is maximum. For example, this part is whatever you are seeing, this part you can consider it as the nucleus. See, this all this region where I have highlighted with the red color. So that high density is what? The probability of finding an electron. This region is what? Complete region is probability of finding electron. So where we can able to find the electron, 3-dimensional space around this nucleus is considered as orbital. Hope it is clear. Okay. So now what we have to understand here is it defines the probability of finding electron and does not define definite path of electron. See, in the Bohr's model we have studied, there are circular paths around the nucleus, something like this. Circular paths we have told. Here orbital is not defining the circular path. It is defining what? Probability, the region of finding electron where it has maximum. That is what? Defined by orbital. Okay, this is what? Orbit. Hope it is clear the difference between orbit and orbital. Okay, now, yeah. So now what are the 3 quantum numbers we got? One is N, another one is L, and another one is ML we have right now. And one more new quantum number here externally added is MS, or simply S I can say. So what are these? These are the set of 4 numbers which helps us to get complete information about electron in an atom. So for example, I am a person, like if someone want to express my identity or my location, how do they express? So he is from India and he is from Telangana and he is from Hyderabad, and now currently in NEET World Hyderabad Institute, Narayanguda Institute, something like this. See, one by one they have to say right now. So similar to that, so N gives information and later L and ML and MS. So this is what overall we can get a complete information about the location of that electron. Hope it is clear. So it will give all the information about electron in an atom, this set of 4 numbers called quantum numbers. Okay, so one is the set of 4 quantum numbers required to define an electron in an atom completely. Okay, so one is principal quantum number N and other one is azimuthal quantum number L and magnetic quantum number ML. The next spin quantum number MS or simply S. Okay, yes. Let us move one by one. Let us read this one by one. See, principal quantum number given by Bohr, Niels Bohr. So what he says, what this principal quantum number N says, it tells us the information about the radius or the size or the energy of that particular electron in which it is present. See, it tells about the energy of the shell in which that electron is present. Okay, so these N values are like 1, 2, 3, 4, so on. And also what I told you, so N value gives us, what N value gives us? Energy. I told you one thing is energy and the second one is size. Okay, so size. For example, these 2 things increases, energy and size increases with increase in N value, with increase in N value. For example, I am giving you 2s, 3s. See, N value here it is 2, here it is 3. So energy also increases as N value increases. So energy of 3s is greater than 2s. Something like this you should understand. Okay. Now one more thing. See, in case of hydrogen atom, now in Bohr model we have studied that. What is the limitation of Bohr model? See, Bohr model is applicable to only single electron species. Now it means we have multi-electron species, single electron species. It means if the atom contains only one electron, atom or ion contains only one electron, we can say it as single electron. And multi-electron means it should contain more than one electron, like helium, lithium, beryllium, boron, carbon, nitrogen. All of them have what? More the number of electrons, like instead of having 1 they will be having 2, 3, 4 like that now, based on its atomic number. So for them we should follow different order, and for single electron we should follow different order while giving its energy level orders. So what is that? See, for single electron species, for hydrogen like species, okay, so what you need to do is the energy value depends only upon the value of n. So as n value increases, their energy also increases. For example, 1s, 2s, 2p, 3s, we are writing something like this. Okay, now tell me what about their energies. See, here n value is 1, here it is 2. So as n value increase, its energy also increases. Here also 2, here also 2. So their energies are equal. So now these 2, 3. So this is greater, na? It has more energy. Now what you can understand from here, so these orbitals which have same n value will have same energy in case of single electron systems. Okay, so these energy levels are same now. So you should call these orbitals or these shells as degenerate energy states or degenerate orbitals. What you should say? Degenerate orbitals. This orbitals with the same energy are called degenerate orbitals. There is a JEE advanced question on this concept only. Just try to learn this now. Okay, try to understand this. Okay, I will solve those questions in the upcoming sessions, in the next session itself. Okay, now for multi-electron system, energy depends upon two things. One is principal quantum number n, and another one is azimuthal quantum number L. So n plus L value you should consider for multi-electron system. If I consider these orbitals for multi-electron system, like 1s, 2s, 2p, 3s. Now tell me, if I ask you what is the order of their energies. See, here we have 3s now. So 3s means its n value is 3 only, and its L value will be 0. I will tell you about that L value. Okay, 0. Okay, here this is 2 n value, and for p L will be 1. So here also it is 3, and here for this it is 2 and L value is 0. Here it is 1 and L value is 0. So now which is having more n plus L value? So it is 3 here and here. So whenever we have same n plus L values, consider the one which is having higher n value, greater will be its energy. Therefore 3s is in higher energy state, okay, or more having more energy. Then out of these 2, this is more energy, okay, and out of this 2, this is 2, so it will be more. See, here it is equal, but in this case 2s 2p is not having equal energies. Do you got the difference? Here if it is single electron, these are degenerate states, but here for multi-electron, these are not degenerates. These are having different energies. It depends upon what values, n and L values. Remember this in case of multi-electron system. Consider this rule, after that this rule. These rules are called Bohr-Bury rules. Okay, hope it is also clear up to here. Let us move forward. And you know, maximum number of electrons present in a shell, you can use this formula. Maximum number of electrons present in a shell is 2n square, and maximum number of orbitals in a shell, if someone asks you, shell is equals to n square. For example, n value is 1, shell number 1, n equals to 1. So number of orbitals in that will be 1 only. For n equals to 2, so it is 2 square now. So 2 square means how many orbitals? We have 4 orbitals. What are those? So one is 2s, for value of 2, it will be 2s and 2p. So this 2p contains 3 orbitals like px, py, pz, and this s orbital. Total how many orbitals we are seeing? How many boxes here? 1, 2, 3, 4. No, that's why it is 4. So for n equals to 3, tell me how many are possible? So 3 square, 9. What are those 9? So 1 from 3s, and 3 from 3p, and 5 from 3d. Hope it is clear. Okay, and I will tell you more clearly. Just hold on few more minutes, it will be more clear to you. Okay, next here azimuthal quantum number we have. This is given by whom? It is given by Sommerfeld. The previous one is given by Niels Bohr. Here it is Sommerfeld. So what is this? It is a secondary quantum number or subsidiary quantum number. Okay, so now it is indicated with symbol L. Okay, so what is the use of this? It the number of subshells present in an energy level given by this azimuthal quantum number. Number of subshell means what? See, 2 things or 3 things you should be clear. One is shell. In this shell we have subshell. Okay, and in this subshell we have orbitals. It should be clear with this. Okay, shell indicated with L, N, and subshell indicated with L value. Okay, in that we have orbitals. Okay, so now see here, in a particular shell how many subshells are present, that thing also should be clear. See, for first shell n is 1 right now, so for n equals to 1, number of subshells here from 0 to n minus 1 level, how many possible, that many are taken as it's a subshells. For example, second shell, if I say n value is 2 now, okay, so n value 2 means n minus 1 means 0 comma 1 comma 2 minus 1 means 1 only, no, that's it. Okay, for third shell n is 3, okay, it varies from 0 1 2 because n minus 1 means 3 minus 1 is 2, so 0 1 2, so 0 means we have L values like 0 1 2, so if L value is 0 you should say it as S subshell, if L value is 1 you should say it as P subshell, if n value is 2 you should say it as D subshell. Hope it is clear. See, based on shell number we are saying what are the subshells present in it right now. So S, P, D are the subshells. Again in subshells what I am saying, orbitals. Okay, so now what are the orbitals present, we will see that also. See, just read here the number of subshells present in an energy level, yes, given here, okay, and angular momentum of electron present in a subshell. So what is this angular momentum? I am indicating angular momentum with NL is equals to root over L into L plus 1 h by 2 pi. So what is this L value here? For S orbital L is 0, for P orbital L is 1, for D orbital L is 2. For what is the angular momentum of S orbital? If I ask you, what you should do? So NL is equals to root over L value for S orbital is 0, no? 0 into something, it will be 0. For P orbital L value is 1, so 1 into 1 plus 1, so root 2 into h by 2 pi. This will be the angular momentum for P orbital. Okay, this is for P. Like that you should calculate. Next, shape of various subshells present in the same shell. So what is the shape of S subshell, P subshell? Like that also it is given by L value only. Okay, I will show you the shapes. And relative energies of various subshells. Okay, relative energies, just now I told now for multi-electron system you should consider N plus L value, not just N value. Okay, next here you can see probability density plots. Just now you have seen here L value gives us shapes of various subshells present in the shell. See, S orbital is having, if this is a nucleus, see electron density is distributed like this. So we have something like spherical shape for S orbital. Okay, and for P orbital if you see, we got something like a dumbbell shape like this right now. So what is the shape of P orbital? It is like a dumbbell like this. Okay, and what about D? See, one dumbbell and this second dumbbell. So you can write it as double dumbbell shape for D orbital. Hope this is clear. So subshells gives us the shapes of their shapes of L value gives the shapes of the subshells also. So L gives the shapes of subshells. Okay, next. So for value of L, if it is 0, S subshell we are saying. If it is 1, we are saying P. If it is 2, we are saying D. If it is 3, we are saying F, like that. Okay, for G it should be 4. Okay, like this. Okay, next we have magnetic quantum number indicated with M and given by Linde. So what is it? See, for a subshell S, for a subshell L, how many magnetic quantum numbers are possible? We will see this. That is indicated with ML. Okay, so for ML, what exactly it is? It gives the information about spatial orientation of orbital with respect to the standard coordinate axis. For example, here for a given L value, ML values will be from minus L to plus L. For example, I have L equals to 2. What are the possible ML values? That will be minus 2 to plus 2. From minus 2 to plus 2 you should write minus 2, minus 1, 0, plus 1 and plus 2. These are the ml values possible. So how many ml values we got? 1, 2, 3, 4, 5. Right now, so you can write a formula, number of subshells, number of orbitals in a subshell is equals to 2l plus 1. So what is this 2 here, 2 l here? L is the subshell number. For example, I am talking about the D subshell. So D subshell L value is 2 now, right here 2 plus 1. So total number of orbitals present in that subshell, D subshell is how many? 5. So that is what we are saying, minus 2, minus 1, 0, plus 1, plus 2. Or you are indicating them as dxy, dyz, dxz and dx square y square, dz square. These are the orbitals you are indicating now. So these are the 5 d orbitals. Okay. Similarly, for S subshell L value 0 now, so you will be having only one orbital here. So number of orbital is 1. For P subshell L value is 1 now, so 2 into 1 plus 1, 3. So it has minus 1, 0, plus 1. So 3 orbitals are there. In D we have 5 orbitals. In F subshell we have 7 orbitals. Okay, and you know each orbital can accommodate maximum of 2 electrons. Therefore, maximum number of electrons in a shell is equals to 2 into 2l plus 1 you can write, because this number gives number of orbitals in a subshell. Okay, and multiply with 2 gives what? Each orbital can accommodate 2 electrons, maximum number of electrons in a subshell. Okay, yes, let us move forward. Yes, look at here, shape. What is the shape of s orbital? It is spherical. So spherical means symmetric around the nucleus now. Therefore I can say it is non-directional in nature. Okay, it is symmetric in all directions. Now what about p orbitals and d orbitals? See, p orbital is having directional nature. It is along the z axis now, so it is in one particular direction. And what is the shape? Dumbbell shape. Like that, all p orbitals are in directional in nature, whereas d are double dumbbell shapes, and these are also directional in nature. See, it is having double dumbbell shape, and you know they will ask what is the angle of orientation of dyz. So what is the angle here? So in between z and y axis we have dyz now. So it means what is the angle they are making here? It is making around 45 degrees right now. So this should be the answer. And what is the angle between the two orbitals in dx square y square? See, here it is how much? One is like this and another one is like this. See, what is the angle here between this? 90 degrees. Okay, so that is also a basic question you can expect. So what are the non-axial d orbitals? dxy, dxz, dyz are the non-axial because they are in between the axis, whereas axial d orbitals are dz square y square and dz square x square, dy square z y square and x square, and dz square. So these are the two axial d orbital, dx square y square and dz square. Okay, next, fourth quantum number here we have is spin quantum number given as s or ms. So what it says? So it says spin of electron. See, an electron in an atom not only moves around the nucleus but also spins about its own axis. Okay, so now since electron can have a clockwise spin or anti-clockwise spin, now for clockwise or anti-clockwise you can say plus half and minus half. Okay, if you are saying for clockwise plus half and for anti-clockwise it should be minus half, or vice versa you can take. Okay, so this is a fourth quantum number. So this quantum number helps us to explain magnetic properties of a substance. What are this magnetic property? If it contains any unpaired electrons, if it contains any unpaired electrons are present, unpaired electrons, so you can say it is paramagnetic. Okay, and no unpaired electrons you can say diamagnetic. Okay, now for paramagnetic species, they are magnetically active. It means they have some magnetic moment. The spin only magnetic moment mu s is calculated using this formula, root over n into n plus 2 Bohr magnetons. Okay, so what is this n here? N represents number of unpaired electrons. For example, here I am saying a species having d5 electronic configuration. Okay, so d5 means what you should write? 5 d orbitals are there. 1, 2, 3, 4, 5 electrons are filled here. So how many unpaired electrons are there? 5. If I say d6, the 6th electron should come here. Now how many unpaired electrons are there? See, these 2 are paired and remaining 4 are unpaired. So number of unpaired electrons in d6 case is 4. Hope it is clear. For d5 it should be 5 electrons like this. Okay, now n value is 5 in case of d5, 5 unpaired electrons. So put that 5 over here. So mu s, spin only magnetic moment, will be 5 into 5 plus 2, 7 Bohr magnetons. So root 35 Bohr magnetons. So you can say around 5.85 Bohr magnetons as your answer. Mu s, spin only magnetic moment. Hope this is also clear. Now I told you angular magnetic moment like NL right now. So I told you that L into L plus 1 h by 2 pi. Here spin magnetic momentum, you can calculate Ns is equals to root over S into S plus 1 h by 2 pi. So what is this S? This total spin. What is the total spin? For example, here I am saying 5 electrons now. So all of them are having same spin, positive spin now. So are positive or negative spin. Only one single spin they have now. So 5 electrons, all of them are as same spin. So total spin value will be equals to S equals to 5 by 2 you should say. Okay, so take S as 5 by 2 and simplify if they ask for spin magnetic momentum. Okay. Next, if the 2 electrons are with opposite spin in any of this orbital, then you should say one is plus half and another one is minus half. The overall spin value will be 0. Hope this is clear. For example, I am saying P2 electronic configuration. P2, we know 3 p orbitals are there, one electron here, another here. Okay, so now what is the spin you will get here? So half plus half, it will be 1. If they are with opposite spin like this in the same shell, same orbital, so what happens to its spin? Minus half and plus half becomes 0. And by following Hund's rule of maximum multiplicity, this is a proper representation and not this one. Okay, now at 1:30 I will be again coming to the live to discuss numericals on the previous year questions on this quantum numbers only. So just stay connected with this channel, just hold for 5 more minutes. I will be starting the live again. So rejoin and you can learn the new concepts and also questions based on these quantum numbers. Okay, so stay connected with us. Thank you.